Discussing
how much like geometry I remember.
I remember this first phrase
I don't remember any of geometry. I should not have passed I basically passed geometry in high school because of
Halfway through my 8th grade year, my friend told my sister and I out of school. She was halfway through her freshman year of high school. Went to Mexico. Did jack shit for online school because online school was horrendous. Then we moved back here and COVID started. So you're still going to school. I essentially did neurons high school except for freshman year. Studied for a week, got my GED, and now I'm in college. I took essentially, okay, college algebra was the first math class I took in like 5 years. And I did it as a plus course. It was so long. It was like 3.5 hours per class section. Sessions twice a week from 5 p.m. to 8:30.
I was homeschooled through all of high school, and I basically cheated through geometry because I didn't understand any of it.
Yeah, no, I technically never saw it.
Because geometry was hellish and I didn't understand anything that was going on.
The person was actually taking here.
Okay, everyone, let's go. So it was brought to my attention, what was your name, sir? Miguel. Miguel brought to, wanted clarification on me mentioning that there are 3 types of multiplication, involving vectors. And just to be clear, there are only 2 operations that we consider multiplication, 2 operations between 2 vectors. Like if you want to combine 2 vectors together, there's only the dot and the cross product. But I said 3 because I'm saying if you want to think about the different types of multiplications that could involve vectors, scalar multiplication is another type, but that's between a number and a vector. So I guess there could be some question with if you're taking linear algebra, right, or something like that. Okay. All right. Any questions before I begin?
No.
Okay.
No.
Last class, I ended with us looking at 3 points in space and trying to figure out whether or not the triangle connecting those 3 points was a right triangle. So I didn't finish the problem, but we at least set up how you would do it, right? You create vectors, and then you dot them, and then you hope to get a 0. Did anyone try it? Anyone go off and try it their own? No? Okay, we'll leave it as an open question then. All right, we're moving on. So what I'd like us to consider now is 2 vectors. Now this can be either 2-dimensional space or 3-dimensional space. For simplicity's sake, I'm going to do it on 2-dimensional. So I have a red vector here, right? I can change the length of it, direction. I have a blue vector. we want to talk about what is called the projection of the blue vector onto the red vector. So this idea of somehow projecting this blue one onto the red one. And the idea is this. It's kind of hard to explain. Well, for me, I look at it as like a shadow. All right, so if you take your two vectors, say you have two vectors like that, and let's say we want to project this white one here onto this one, we're going to imagine dropping a perpendicular line down straight and then looking at the vector that goes from there to there. So it'd be like if we had a light source at infinity way up there and we just shined the light straight down, it would be the shadow cast onto this, right? So it would look exactly like, we're doing the blue onto the red. It would look like that vector right there. Can y'all kind of see that? It's purple. Yeah. But it's that dropping that perpendicular from the blue one down onto the red one.
It's perpendicular to the one that's being projected onto.
It is, this vector is the projection vector. It's, you said it's perpendicular to what?
The one that's being projected onto, or the other.
Well, the purple and the red one are parallel.
Yes, but
not perpendicular.
But the line that's being drawn.
Okay, this would be perpendicular, yes.
So when you said perpendicular the first time, I thought from the one projecting, and I'm like, that fits you way out further.
Yeah.
But yeah.
So this vector here, right, is called the projection vector, all right? And let's do it the other way around. Can you project the red onto the blue? Yes. Now, if you do that, let me get rid of the stuff here. So if I project the red one onto the blue one, wouldn't it be like somewhere over here? It wouldn't be on that blue one, would it?
No.
It would look like this. You see that? It would actually be longer than blue, the blue one. But it is still what we consider to be the vector projection. Does that make sense geometrically? You have a question?
Is the length or magnitude of the projected vector different?
Is the length or magnitude of the projected vector different from the one that we are the red one then? It'll be different. It'll be different. And actually, that's actually the first question I'm going to ask now, is that if we take a vector and project it onto another vector, can we find the length of that new projection vector? And then if we can find its length, maybe we can actually find the vector itself. Because remember, there's a difference between a vector and a length of a vector, right? So I'm going to give you formulas and stuff like that, but I want to see if we can come up with the formulas on our own, if we can actually derive the formulas. So let me go with some color here. Let's say we have a vector, I'm going to call it u. Okay, and I'm going to project that onto another vector v. And just, again, to keep things simple, I'm going to draw my v so that it's longer than the u, and I'm going to draw it so the v points to the right, so it looks easy for us to draw triangles and things like that. But this is arbitrary. This can be anywhere in three-dimensional space, two-dimensional space, all right? And what I want to know is what I get when I project. I'm going to project the u onto the vector v. And let me draw you that new vector. I never gave you your purple marker back last time. And you probably won't ever get it back. Ooh. All right, you can just go get more from the lab, right? Okay, so there we go. That right there, I'm going to call that vector. Here comes the sign-in sheet. I think I forgot to pass this around last time, didn't I? It's no big deal. It's Cal 3. If you're not here, you're not here, right? Oh, got it. Okay, so that vector right there is the projection vector. Let's call it P. Let's call it P for projection. That sound good? All right, the first thing I want to do is talk about what its length is, all right? Let's find out, see if we can figure out how long this projection vector is. So the length of P, well, here's how I'm going to do it. It's going to be really weird. This is why I like to show this. It's going to seem not very natural the way I go about this. Do you agree that there's an angle between those, right? We can call that theta. And going back to what we know from pre-cal, right? Pre-calculus, if you have a circle of radius r, right? and you have not the unit circle, right? Circle radius r, and you go to some arbitrary point on that circle, then that's r, right? If this is theta, then the ordered pair for that point is not cosine theta sine theta anymore. What is it? R cosine theta, r sine theta. So you have to put an r in front of the two trig functions. R cosine theta, r sine theta. Does that ring a bell?
Yes.
Recall seeing that ever before? Now if it's the unit circle, right, if the radius is 1, then this is just cosine theta sine theta.
Yeah, because unit circle R is 1.
R is 1. But arbitrarily, this is what it is, yes?
If you take those points, you just take out R, and then you just scale it up however it is.
Say again?
You would just scale it, you would scale your points by your radius.
Yeah,
That-
yeah.
that's what
Could you take it out, or out, or is it in principle inside?
No, you have to have it in. Oh, no, yeah, no, you don't take that, because you don't scale a point. You don't scale a point. You don't distribute numbers through points. Okay, we good?
because they're not really being added.
We good? All right, so now, with that idea, imagine now that, try to draw it in here. The blue vector right here is going to be kind of like this right here. All right, and then the purple vector is the projection down like this. And then my red vector just goes out. I don't even care where that is, all right? Could I look at it this way?
Yes.
The blue vector is like on some circle, and then the projection of it straight down is this. And I want to know that length, don't I? So to know the length, I just need to know the x-coordinate of that, right? Which would be what? R cosine theta, right? Okay. So what is r for us? In this picture, what is r?
Be the magnitude of
Magnitude of it, right? This is the magnitude of u, the u vector, right? And then the theta is just theta. So do you all agree that the magnitude of p, that's this distance from here to here, is just the magnitude of that times cosine of the angle, isn't it?
But you would already have a direction needed, you'd have it equated.
Say that again.
Wouldn't you need to have a direction correlated to that?
Well, if somebody gives me two vectors, right, I can always find that angle between them using what we did last class, right? There was a formula for it, right? There was a formula. It was basically a dot product formula.
So it's something different, but I'm saying is that R can't be the magnitude. The magnitude of U implies that it's just the length, as opposed
Yeah.
to direction as well.
I'm not considering directions at all. I'm considering lengths of vectors only so that we can look at it more like a triangle, right? And if we look at a triangle, then we can fix it into a circle. So I've got this triangle. I'm getting the x-coordinate, which is r cosine theta. R for us is the length of u, and we're multiplying that times cosine of the angle. Do you all agree with that equation up there? Anyone disagree or want me to clarify?
looks good to me.
Yeah? But in that formula, don't I need to know what the angle is? Yes? I need it? I need to know the angle. I don't feel like finding the angle. The angle is going to be a pain in the butt. So this is kind of the weird part, the cool part, I think, cool part. Let me talk. Let me finish my ideas before you interject, please. All right? You're free to interject, but just let me at least finish what I'm saying.
I'm used to being muted on a Zoom call in your classes, so.
Hold on. Okay. All right, so I'm going to do something weird here. I'm going to multiply both sides of this equation by the magnitude of v. By the magnitude of v. And I'm going to put it right after the magnitude of u. Am I allowed to do that? As long as the magnitude of v is not 0, so as long as v isn't a 0 vector, I can multiply both sides by the magnitude of v, which is just a number, isn't it? I can do that? I did that for a particular reason. Look at the right-hand side of that equation. What is it? It's the dot product, isn't it? That's u dot v. By definition from last class, this is what u dot v is. That's why I introduced it, right? So that I could get it to look like u dot v. Right? So now I have this is equal to u dot v. And I wanted the magnitude of P, right? So I'm just going to divide both sides by the magnitude of V now.
Yeah, it's a magnitude.
And the advantage to using this formula, over this formula is what? I don't need the angle. And the dot product is easy to do, right? We all agreed last class dot products are easy to do. And magnitudes are relatively easy. They have square roots, but that's a pretty clean way of doing it, right? So that means that if you give me two vectors and I want to project one of them onto the other, what I'm going to do is I'm going to take the dot product of the two vectors and I'm going to divide it by the length of the vector I am projecting. Which one? Which one is I'm doing the length of? The length of which one? On the one I'm projecting onto. So if I'm projecting onto V, that's the one I'm going to divide by here, the length of that one. Got it? Okay, so we have a formula, and if you look in the notes, I provide you the formula, all right? Actually, it's right here. We have a name for this, okay? The length of that vector, hold on just a second, the length of that vector is called the component of U onto V, or comp U onto V. Okay, comp of U onto V. This is the notation we use for it. So you're taking the component of U, and then see that little subscript? That's what you're projecting onto. Right, so U onto V, and that is by definition, or not by definition, but what we just convinced ourselves, hopefully, is this formula right here. Now notice in that formula I have the U dot V backwards from what I did here, right? They're backwards. Does that matter? Dot products are commutative, right? That was a property from last class, so there's your formula, all right? Now, your question?
So it's originally taking the dot product of, I'm trying to hold the term unit vector of V. Because could you, I'm trying to remember, because it could just be vector V over the magnitude of V dot U. So isn't that just like taking the unit vector dot the projection vector? Or the vector you want to project onto it?
Let me put it up here, and then I'll try and understand what you're saying. Okay, are you saying that you're taking that, which is just a unit vector in the direction of V, and then you're dotting it with U?
Yeah. Is that just basically what you're doing?
Are you allowed to do that? What do you think? Are you allowed to do what you just did? Is this multiplication like our standard multiplication like this? Like if I had 3x over x, right? I can reduce this, I can cancel these x's out because this multiplication up here allows me to do that. Are you allowed to do the same thing with the dot product? Can you just divide this out and separate it? What do you think? Probably not, because it's not the same type of multiplication as scalar multiplication. Now, you are on the right track for something, which is if we want to try and find P itself as a vector. Like all we've done right now is found its length, right? So let me develop the thing for finding the vector itself, and you'll see we're going to use the unit vector. Okay, I got to draw my picture again. We were projecting blue. Blue? That's the only blue I have up here? Okay. It was blue onto the red, right? V, and we have this projection vector right there, which we called P, and we now know how to find its length, right? You just leave that, thank you. I've got plenty more over here. We know how to find the length of that, but what about P itself? How do we find P itself? So what about this idea? We know everything about V, right? We're given V. So isn't P parallel to V? They're parallel to one another? Yeah? So the first thing I'm going to do is I'm going to find a vector that points in the same direction as V, but has a unit length. All right? So how would I find that? How would I find a unit vector that points in the same direction as V? Take the V and divide it by its own magnitude, right? This would give me a unit vector in same direction as V. So I'm going to draw that over here, right? It would be somewhere over here. It would be pointed this way. And all I need to tell you now is that the length of that is 1, right? The length of that is 1. Now, to get this vector, what do I do? Scale that black vector by how much? The magnitude of P, right? Don't I just take that black vector and multiply it times how long P is? And that should give me a vector that's pointing in the same direction as V, but has a length, this length of P. So let me do that. I'm going to take this vector here. I'm going to take the length of P and multiply it times the V over its own length. And that right there should be the vector P. Right? It's the length of this times that black vector. Almost there, not quite there yet. What is P? Magnitude of P, we just defined that, didn't we? It was what? It was U dotted with V over magnitude of V, right? So that's this. And then what's this? We'll just put it right next to it, times V over magnitude of V. That, right? I know this looks terrible, but do y'all understand where the pieces are coming from? One last thing. Because this is a number and this is a number and they're exactly the same, I'm going to move them over to the left. And I'm going to have U dot V on top. That's a number, isn't it? U dot V is a number. And I'm dividing it by the magnitude of V, but that's squared because there's 2 of them. And then I'm multiplying, not dot product. I'm multiplying that times V. That should be the projection vector. This right here is a number. And I'm multiplying a number times a vector. What happens when you take a number and multiply times a vector? It either stretches it or shrinks it, right? Or flips it over. But in this case, we're multiplying this vector V by something that's going to generate that purple vector. And we did it by first creating the black vector and then scaling it by the length of P. I hope that makes sense. If it didn't make sense, it's okay, because there's the formula and it's in the notes and we can just use it, all right? Yes, go ahead.
That leads me to a very important question, which is, with all of these formulas here, how many of these are we going to be allowed to have on notes in tests? Because, just memorize them?
There's not an expectation that you memorize all the formulas for this class. It's too much, even for really good memorization, or people who are good at memorization. It's too much. The chapter 13 formulas, I think, is like 13 pages long, right? So
there's some formulas.
So most likely your exam 2 is going to be not an open note test, but it'll be probably like an open formula test where I will tell you what you can and cannot have. But you will not have to put these all into memory, all right? The projection of U onto V, this is in your notes, but I'm going to put it up here so we have it. It's V dot U over the magnitude of V squared times the vector V. This is your projection vector. See how I used PROJ? Your projection of U onto V. That is a vector, okay? That is a vector. Not to be confused with component of U onto V, which is the the dot product of U and V over the magnitude of V, right? That by itself is just how long P is. Yes?
Sorry, I just got kind of lost. I don't really understand how you ended up getting the magnitude of V squared.
Because this is true multiplication right there. That's not a dot product, okay? And so you have 2 fractions, and then so I'm putting those 2 together. And I'm saying the magnitude of V times magnitude of V, so that's magnitude of V squared.
I think the arrows just threw me off, but okay, yeah, I get it.
Oh, my vector arrows?
No, the ones going from the magnitude of P over to the dot.
Okay, this right here is just that, right?
Right,
And then this is that. And then I multiply them together.
I got it.
Yes?
So how would you visualize this with like an obtuse angle? Because I've seen you been doing this with acute.
Great. So the question is, how do we do this with an obtuse angle? Right? Let's do it. I'm going to erase this because I don't need it anymore. Well, if it's obtuse, then the projection vector should be in the opposite direction, shouldn't it? Than the vector we're projecting on?
Oh. Oh, is that the next?
There we go. So look, I'm going to make this vector longer, and then put this blue on here. Wait a minute, I'm projecting the other way. Let's go blue onto red. There we go. So that's the blue one being projected onto the red. You're asking, what happens if the angle between those two is obtuse? This is a great question because look, we already know what happens if the blue vector is like longer, right? It projects out. Hey guys, come on. I can hear it's distracting to me. Okay, that's all right. I'm just second time. So, all right, past this, right? It's longer. Obtuse, it's back there. So it's almost like you're projecting this blue vector onto an imaginary line that extends in both directions on the red vector. Everyone got that? This makes sense because to do the projection vector, you need a dot product, don't you? Dot products will be positive if the angle between the vectors is acute, and dot products will be negative if the angle between the vectors is obtuse. So we should expect that if that angle is obtuse, that we're going to get a negative number out here, which means we're going to point that vector, we're going to do a scalar multiple of v that has a negative, so it points in the opposite direction of v. Yes?
So the actual math is going to be the same. Like our formulas.
Nothing changes here.
Nothing.
Absolutely nothing changes
So
here.
it would just be in our drawing it out to understand it that things would change.
That's right.
I forgot if it was 90 degrees.
You forgot what?
If it was 90 degrees. I think
You forgot what the dot product is if it's 90 degrees?
Yeah, so, no, yeah. So,
Don't forget that. That's the one thing I don't want you to forget is that, this is the one thing. If the angle between two vectors is 90 degrees, the dot product is 0. That's what we do to check to see if anything is orthogonal, right? Right, that's that test for orthogonality. All right, here's an example. Find the projection of u onto v and then the component of u onto v given these two vectors. Now, I gave you two-dimensional vectors. Is that all right? We'll do two-dimensional. Do I have another example with 3? No, I don't. Okay, so let's do this. Let's start with the projection of u onto v. So this should be that formula right there, right? So I'm going to take the vector v, which is the vector -3, 7. I'm going to dot it with the vector u, which is the vector 2, 4. I'm going to divide that by the magnitude of which one? Magnitude of v. So I'm going to take magnitude of v is that component squared plus that component squared. Right, that's the magnitude of v. But then I have to do what with it? Square it, right? Because the formula says you take the magnitude of v and you square it. And then multiply that times the vector v itself. So the vector v itself over here is the vector -3, 7. Like that. Everyone see all those pieces together?
Yes.
V dot u over magnitude of v squared times the vector v.
Didn't you already find the comp?
Do what?
Didn't you already find the comp?
Yeah, well, almost. This one is not squared. So when we do the component, it's actually, we will have done most of the work already. All right, this equals. All right, let's do the dot product here. To do dot product, we do this component times this, so that's -6. Let me go ahead and write it down. -6 plus, and then you do 7 times 4, which is 28. And then over, all right, 9 plus 49, right? 9 plus 49, what's 9 plus 49? 58.
58, yeah.
Square root of 58, but then squared. So just 58?
Yeah, just 58.
Okay, and then that's times the vector -3, 7. Please, again, recognize that's just a scalar, isn't it? This is a number sitting in front of the vector v, which is the number that's going to stretch it appropriately to get that projection vector where we want it.
Oh, that's pretty cool. I didn't
Right.
notice that at first.
So now this right here is 22 over 58. And then we can reduce that fraction, can't we? 11 over 29, yeah, 11 over 29. And then negative 3, 7. And then because this is scalar multiplication, I can just multiply that 11 over 29 through the angled brackets. I mean, I'm getting a little loose on my language there, but that's essentially how scalar multiplication works. You just multiply this number times each of the components. So we get our final answer, which is
77.
negative 33 over 29. This is a vector still. And then comma 77 over 29. That's the vector right there. If we draw that vector, it should be the projection of the u onto the v. Yes?
Where did the distance formula come from under the spectrum?
Magnitude of, I think we did that 10.2.
So it's about 2.5. I just look at that.
Yeah, 10.2, very first.
Right there. 10.2.14. The length of a vector in two-dimensional space, and then the length of a vector in 3D is just one more component you have to square and add. Good? Okay. All right. Any other questions on that one right there? We've answered the first part, right? We've got the projection of u onto v. Now we need the component, right? The component. Now we have two options. We can go to the formula and crank out the formula if we'd like, right? That's one way. Or we can just use the fact that we know it's the length of that vector, right? The component is just how long that vector is. So we could use this formula I just showed you, the square root of each of those components squared, add them up, take the square root, or I just use this. So what do y'all want to do? I don't really care.
I'd rather use a component formula.
You'd rather use this? We already kind of did this, right? So it would be easier, I think, if we just use this. But either way works. So let me put it,
I don't want
put
to
it right here.
work with those fractions.
Yeah. I'm doing the component of v onto u. No, u onto v. Hey, everyone, it would be different if I did it the other way, wouldn't it?
Yeah, because
If I did the component of v onto u is a completely different thing.
magnitude of u on the bottom, right?
Well, you would have to get this as well. I mean, like everything would be different, right? What you're projecting on what. All right.
Projection, yeah, change that.
A lot of things change because this changes.
That'd be u, wouldn't also it be times
U
as well?
Yep. Yep.
Oh.
Everything changes. All right. So this one right here.